All right, so now I'm going to prove the Poincare theorem, which basically says that the Hamiltonian flow is symplectic. All right, so theorem. So if H is twice differentiable, twice continuously differentiable, then the flow map phi of t of the Hamiltonian system is symplectic. Okay. All right. And of course, symplecticity basically means that the linearization of this. Okay. So. Let's write that. Transpose J of times the linearization is equal to J, right? Okay, so let's prove this. All right, so you have a Hamiltonian system. So my notation is a little bit different from the textbook because in my notation, position is first and then momentum is second. All right, so anyway, so what happens is that y prime is equal to j gradient of the Hamiltonian, depending on y, right, where y is equal to q and p. All right, and j, if you recall, is equal to this sort of 2n, well, sorry, 2s, well, 2D by 2D matrix, which looks like the following. Okay, and it gives you that equations, right? So this is just this set of equations here. All right, okay, so you have that. And then you denote the Jacobian of the map by sort of capital Phi t, right? Okay, and then we observe the following, right? That the time rate of change of the map, right? Okay, applied to a given point, of course, is a solution curve of the Hamiltonian system, so it satisfies the differential equation in some appropriate sense, J gradient H. Okay. All right. And once you have this, it's like then we can say something about the Jacobian, it's like of the map, right? And so this implies that the time rate of change of the linearization or the Jacobian, right, is equal to J nabla squared H. Okay, and then so this is, you're applying essentially the product rule, right? Sorry, the chain rule, right? So you have to differentiate this thing, and then you have to differentiate the inside. Okay, all right. So, so yeah, so this is yeah. well, you're sort of mixing the order of the derivatives in essence. Yep. Anyhow, okay, so so now that you have a equation for how the Jacobian, it's like changes as a function of time, we can look at this condition. So obviously this condition is trivially satisfied at t equals to 0, because at t equals to 0, the flow map is the identity, and so its linearization is the identity matrix as well. And so this condition is trivially satisfied at t equals to 0. So what you want to do is you want to look at, as we've seen many times before, you want to look at the time rate of change of this left-hand side, and you basically want to show that it's identically 0. And then that together with the fact that at t equals to 0, this thing is just trivially j, gives you what we need to prove. Okay, so you compute time derivative of that left-hand side. Okay. And then you just apply the product rule to that, using the fact that the J matrix is constant as well. So that just gives you the time rate of change of this Jacobian transpose J, the Jacobian plus the transpose of the Jacobian J, the time rate of change of it. Okay, and then you, of course, use this relationship here. Okay, so that's equal to, okay, so when you transpose, it's like you reverse the order and you transpose everything. Okay, I'm going to drop the dependencies now. Okay. And of course, it's like the Hessian is symmetric, right, because of the equality of mixed partials. Okay, so its transpose is itself. Okay, then you have J transpose. Oops. Times J times this flow. All right, that's one term. And then there's the second term, which is nabla squared times the Jacobian. Okay. Okay, and you can check that J transpose times J is the okay. So J transpose is 0 minus identity 0 times 0 identity minus identity 0. Right. So this times this plus this times this, that's the identity. This times this plus this times this is 0. This times this plus, okay, this times this plus this times this is 0. And then this times this plus this times this is the identity. All right, so that's just the identity matrix. All right, so this is just J transpose J. And then you can check that J squared is negative of the identity. Okay, so that's all right. Okay, minus All right, and of course those two are the same except for the sign, so that's just 0. Okay. And as I said, it's like at time equals to 0. This is trivially true, right? Because at t equals to 0, right, the linearization, it's like of the map, the flow map at time 0 is just the identity, which means that at time 0 you have the property that this is just identity transpose J identity, which is just J. All right, that together with the condition that this time derivative is 0 means then that you have the symplecticity condition for t greater than or equal to 0, right, which is what you wanted to prove. Okay, all right, so that shows that it shows Poincare's theorem, which says that a Hamiltonian system is symplectic, or the flow of a Hamiltonian system is symplectic. All right, so let's just stop here.